control systems, one of the most important questions engineers ask is the system stable or not? A stable system responds to input and eventually settles down, while an unstable system behaves unpredictably or can even fail. In this video, we will explain the concept of stability, its importance, and how to determine it using the Routh-Hurwitz criterion, followed by a step-by-step example.
About what stability is all about. So stability refers to the ability of a system to return to its equilibrium or steady state condition after being disturbed. So from a system performance perspective, stability is one of the most important requirements because an unstable system is practically useless no matter how fast or accurate it appears initially. So engineers often analyze stability using methods like the Routh-Hurwitz criterion or by examining the location of system poles in the S-plane. For a system to be stable, all poles must lie in the left half of the S-plane, meaning they all have negative real parts. So stability also affects how a system responds to input. So a stable system produces a predictable and controlled output, while an unstable system may oscillate or diverge. So even marginally stable system can produce sustained oscillations, which may not be desirable in real applications.
Imagine a pacemaker that doesn't have a steady rhythm and it randomly starts or stops. Instead of helping the heart to beat properly, it could lead to very serious complications and even be life-threatening. Now think of an infusion pump which suddenly speeds up and slows down. It could deliver medication in very unpredictable doses and put the patient at risk because it can either deliver too much or too little medication. Control systems are very important in biomedical engineering because without them, devices can be unpredictable and reliable. So engineers must ensure consistency and predictability, hence stability, in biomedical engineering devices.
Stability is actually a very important concept in control systems because it determines how safe or dangerous a system is. A stable system is one that receives inputs and settles at a steady value, whilst an unstable system goes its outputs uncontrollably. Stability plays a very critical role in biomedical engineering when it comes to the operation of medical devices. For example, infusion pumps must deliver drugs at controlled and consistent rates. And when we consider a device like the ventilator, it must ensure that there's steady airflow and pressure when supporting patients breathing to avoid damage to the lungs. Lastly, when you consider a machine like the ECG monitors, it ensures that we gain accurate signals for diagnosis. So overall, this concept of stability is very essential in the operation of medical devices. It ensures consistency and safety of patients, which is our goal.
Talking about ways of determining stability of a system, we have the step response method. With the step response method, if the system settles after a disturbance, it means it is stable. But if it continues to oscillate after it has been affected by a disturbance, it means it is unstable. You have the Routh-Hurwitz method. With that one, we check the signs in front of the system's equation. If the signs are all positive, the system is stable. But if any of the equations has a negative in front of it, the system is unstable. We also have the roots location method. If all the roots are located on the left-hand side of the plane, it means the system is stable. But if any of the roots is located on the right-hand side, the system is unstable.
Speaking on the RH criteria, the RH criteria is basically meant for us to, it helps us to determine whether a system is stable or not by solving for its characteristic equation. So let's say, for example, the question they gave us, instead of us solving the roots directly, we write the coefficients in the question, the coefficient given to all the coefficients in the question in a table form, forming a root array that will help us determine whether a system is stable or not. So in this sense, after we've set up the table, after we've drawn the table out, the first column of the table and the coefficient side. So the table is divided into two. We have the powers of S and the coefficient side. So we'll focus on the coefficient side. We'll focus on the coefficient side. all the first values on the first column of the coefficient side, if all of them is positive, it will tell us that the system is stable. But if there's a negative sign on the first column of the coefficient side, then that tells us that the system is stable since there is a change in sign.
We've been given a characteristic equation, which is we are supposed to analyze the system and determine its stability. And one of the methods we are going to use is the RH criteria. We will construct a table and we will analyze the table. Based on the values of the first column, we will determine whether the system is stable or not.
All right, so we are to determine the stability of a system whose characteristic equation is given by s to the power 4 plus 2s squared plus 2s cubed, sorry, plus 6s squared plus 4s plus 1 being equals 0, right? So we are going to solve for that using the RH method or the Routh-Hurwitz method. So we are going to do that by using the root test, right? So with that, we start from s to the power 4, since that is our highest degree, down to x to the power 3, s to the power 2, s to the power 1, and x to the power 0. Right. So we are going to fill the rows this way. We start from the x with the highest degree. So the coefficient of that is 1. Then we have to skip the second term and pick the coefficient of the third term, which is 6. Skip the fourth term, pick that of the fifth term, which is 1. Moving on, we are going to fill in the second row with the coefficient of the skipped terms. So that's 2 and 4. That's that of x cubed and s. Right. So we have to fill in to the very last point. So doing that, we have to find for some values b1, b2, c1, and d1. Right. So we are going to determine that by finding the negative determinant of this section, solve for the other section. So maybe how I'm saying it, you may not get it. So let me solve it as I said so. So we are going to, it will be 1, 6, 2, 4. Multiplying half, multiplying negative of the inverse of the pivot element. So with that, we are going to have 4 minus 12, which will be negative 8, multiplying negative half, and that is going to give us 4, right? So our B1 is 4, our B2 is equal to 1, 1, 2, 0, since we have no term over here. So with that, also multiplying 1 over negative of the pivot element, which is 2. So with that, we have 0 minus 2, multiplying negative half, and that is going to give us 1. So our B2 is 1. Then solving for the B3, C1 is going to be the determinant of whatever matrix will be formed over here. So we have our B1 and B2 by solving this. So we are going to use that one together with this row element to solve for our C1. So that will be 2, 4, 4, 1. Multiplying 1 over 4. That's negative 1 over 4, right? So that is going to be 2 minus 16, which will be negative 14, multiplying negative 1 over 4, and that will give us 3.5. So our C1 is 3.5, right? Moving on, we are going to solve for our D1, which is going to be the matrix form at this section, right? So we know our B1, B2, and C1. So we are going to use that to solve for our D1. So that's going to be 1 over, that's negative 1 over the principal value, which is 3.5, multiplying the determinant of 4, 1, 3.5, 0, since we have no element at this point. So this is going to give us 0 minus 3.5, and that is being multiplied by 1 over 3.5, negative. So with that, we are going to have 1, because negative 3.5 divided by negative 3.5 is going
So
to...
from the RH criterion, we realize that the system becomes stable if and only if the element in the first column has no sign changes. So in our solution, we realize that the pivot column, that's the first column, has no sign change. All of them are positive. Hence, the system is stable. But if there had to be a condition where maybe there was this 4 was negative, that means the system will be unstable because some of the roots will be on the right hand side. But since this one there is no change in sign, that means the system is positive.
Looking at column 1, column 1 being the column of relevance. Column 1 has values 1, 2, 4, 3.5, and 1. All these values are positive. So, by method of prediction, since all the values have the same sign, being positive, we can predict that our system is stable. So, on the S-plane, GW, since all the coefficients of the column of relevance are positive, and on the S-plane, we have our points for plotting being a complex value. So having the real part to be minus zeta omega n plus or minus j omega n square root of 1 minus zeta squared. And because our coefficients from the column of relevance are all positives, without solving the characteristic equation, we can see that all our roots are going to be negatives. Thus, our real part is going to be negative. And if our real part is going to be negative, we are going to have our points on the left-hand side. And if our points are on the left-hand side, we can probably deduce that our system is very stable.